Hi folks, and welcome back to Physics with Captain Rod. I'm making this video here to help you out with your first 3 homework problems here in your Unit 3 homework. So just a quick little review here. These first problems are about impulse and momentum. And just a quick review about this stuff. When you take Newton's second law, right, which is F equals ma, you can rearrange this, and I'm not going to go through all the detail here. Because I did that in other videos about impulse and momentum. But basically you can rearrange this until it looks like this. Mass times V initial plus F delta T equals mass times V final. And these terms are called your momentums, mass times velocity, and momentum is a vector quantity because velocity is a vector. And then this quantity, force times time, is your impulse. And equation-wise, what this is saying is whatever your initial momentum is, plus the impulse added equals your new momentum. Now, a very important detail about that, though, is that momentum is a vector concept, which means you have to apply it by direction. So, as we look at number 1, an 1,800 kilogram car moving at 30 meters per second. So these sets of questions, the first one here is just a calculation. What is the car's momentum? Well, momentum is mass times velocity. And I guess, let's maybe do a quick picture. Here's our car, picture 1, its momentum vector. I'm just going to put it to the right, and now I'm inherently doing right positive. So then you could put a positive number here, and that would mean to the right. Now, what impulse would stop the car? So hopefully you've seen my videos about momentum and impulse. You start by drawing a momentum vector, which I did, and this vector has a magnitude equal to whatever this number is. Then you draw your impulse picture. So the impulse is acting on the car. It has a weight, right? It's not falling, right? It's supported by the ground and normal force. Now it says to stop the car. So if your initial momentum is to the right and you want to stop it, your impulse would have to be to the left. We'll put some sort of F delta T here. Now, the difference between a free body and impulse momentum diagrams is just the time factor. If I take these forces and just put delta T's on them, okay, these are now impulses. And then my picture 2 here, the car is stopped. It has no momentum. So you want to draw a series of pictures. All right, picture 1, initial momentum of the system. That's for this part. Picture 2, your impulse acting on the system. Right? You start with a free body, putting in any external forces acting on the system, just like you normally would in any other free body, and then you just tack times on. Now they're impulses. Then you draw your picture 2 for this part, and because it's stopped, it doesn't have a momentum vector. Now, equation-wise, you've got this momentum minus this impulse equals. And just ask yourself, what is the final momentum or the momentum in that picture? If you solve this correctly, I got 5,400 Newton seconds. Now, I guess actually, to tell you the truth, if we define this momentum right here as a positive number, this should be negative technically. I should go back and actually change that because the impulse has to be in the opposite direction of the initial momentum. Part C, use impulse momentum methods to find the force needed to stop that car. So if you go through and you write your momentum equation, x direction here, and solve for F, you should get about 13,500 newtons. And actually, this is the magnitude of that force. Again, that force is going to end up to the left. I'll just put an arrow for the direction. All right, and then part D, where it says use principles of work and energy. So here you're going to write out a work energy theorem for the car. Your PE1 plus KE1 plus work 1 to 2 equals PE2 plus KE2. And then just go through it term by term. Now this problem doesn't have anything to do with vertical motion. So we can just basically datum these to 0 and not worry about it. And then in picture 2, right, that's this picture, we're not moving anymore. So that should tell you something about that kinetic energy. So really only 2 terms survive here, your KE1 term and your work term. Now your KE1 can be written 1/2 mv1 squared. Now our work term. Look at this picture right there. And keep in mind that the car is moving from left to right. And ask yourself, how much work does that normal do? How much work does the mg do? Keep in mind, they make right angles to the motion. But this force right here, right, that does work by an amount, force times distance. And also keep in mind, this car is moving to the right, but the force is to the left. So the force will show up in this term right there. I got 16,200 newtons. Let's see what you get when you work it out. All right, moving along here. Let's take a look at number 2 here. Let's see. Ooh, oops. It's supposed to be a person. A person throws a 0.6 kilogram basketball horizontally against a wall. So, you know, quick little picture, right? We've got a wall, and we have a picture of a ball moving this way before impact. And I would call that like V1 or V initial or something like that. And then the ball returns at 7 meters per second. So sometime later, the ball's moving this way at some sort of V2. That's 7 meters per second in this example. Now, I don't mean that the ball's physically lower. These are just different time frames. So this is like before, snapshot after. Okay, now, the impulse momentum relationship. Again, remember, mv initial plus f delta t equals mv final. So you draw a picture of the ball somewhere. Maybe, you know, like up here. Now I know I've got this right here, but this is just a picture that's describing the problem. Put a momentum vector on for before the impacts. And if you want, you should be able to calculate a number because you've got a mass and a velocity. Right? Then you draw another picture of the ball showing the impulses. And ask yourself, what is the force direction on the ball? Look at these two velocities, by the way, V1 and V2. And that should tell you which way that force direction is on that ball. Then you draw another picture for the MV final. And again, you have numbers here. You could actually calculate those. Now, the change in, now we start answering these questions. The change in momentum of the ball. Take whatever you have here, that's your final momentum, subtract whatever you have here. That minus your initial momentum, that's going to give you the change in momentum. Part B, what is the impulse delivered to the ball? Once you get this picture done, you should be able to write an equation. It should look virtually just like this, other than you can put numbers in. And this term is the impulse. So basically just solve for that thing in the box there and you'll get the impulse. I got -9 Newton seconds. Now, let me talk directions here. You'll notice when I did part A, see I put this minus sign here, and you'll notice I put relative to V initial. So what I mean by that is I'm calling right positive. This minus sign right here means to the left. Same thing with this one, same thing with this one, and so forth. Let me chat a little bit about part D, okay? What is the change in kinetic energy of the ball? So if we go back to our picture, this picture right here, you should have a velocity, you know, a momentum vector, mv. You should be able to calculate a kinetic energy for that. Then you should be able to calculate a kinetic energy for after the impact. And this says what's the change in kinetic energy? That's the difference between the two. This minus sign here is different than these minus signs. And the reason they're different, these were all vector quantities, so these minus signs had to do with direction. This one is negative because you're going to find that the kinetic energy dropped. It didn't increase, it decreased. So that should be enough, hopefully, to get you through that problem. Let me take a look at the next one here and probably call it a video. Okay, a 0.6 kilogram ball dropped from a height of 2 meters. Then it rebounds to 1.6 meters high. So you need to start this with a series of pictures. Picture 1. The ball starts here at a height, we could call it maybe H1. That's the 1.6 meters. Picture 2. Just before impact with the ground. Again, you notice there's a little daylight right there. That's important. That picture 2 is supposed to be an instant before. Okay, picture 3. Now I'm going to actually move this over to the right here. It's not that anything moved to the right, but I need to, and I don't want to put it right on top of the first picture. Picture 3, the ball has hit the ground, reverse direction. It's now moving up with some sort of speed, maybe V3. Picture 4, it has hit its highest point, where the H4 here would be the 1.6 meters, the H1 being the 2 meters. Okay, so the important thing here, get a series of pictures. I guess I already basically did those for you. Right? Now, start writing equations. So to get the velocity of the ball just before impact, from 1 to 2 here, again, 2 is right before impact. That's a work energy problem. That's basically the PE1 is going to equal the KE2. I got 6.26 meter per second when I worked it out. Part B, where it says the velocity of the ball just after impact. Just after impact, that's this picture, picture 3. Write a work energy equation between 3 and 4. And you'll basically be equating the kinetic energy at position 3 to the potential energy at position 4 to calculate your V3. Okay, part C, find the impulse delivered to the ball. Right, now we need to be thinking impulse and momentum. So remember, your initial momentum, mv initial, plus your impulse, F delta t, equals your final momentum, mv final. I always kind of write that out just to help guide my work. You draw a picture of the ball an instant before impact, and you put a momentum vector on it. And you should be able to calculate a value for that, because you should have velocity just before impact, and we have the ball's momentum. Right, now, you draw another picture for the impulse. So here's a picture of the ball, and you got to think during the contact time with the ground. So ask yourself, what is the force direction between the ground and the ball? And again, on the ball. And then put a force vector on that ball. And then you just tack a time on to make it an impulse. All right, and then basically equals. Then you draw a picture of the ball and you put the final momentum vector in. That's going to be here, picture 3, right after impact. Once you get the pictures right, the equations basically should write themselves. Pick a direction to call positive, doesn't matter which. And then you go, okay, my initial momentum plus my impulse equals my final momentum. That should allow you to find the impulse. And then impulse is force times time. Once you have the impulse, finding the average force on the ball should be no problem. So that video's at 10-12 minutes now. I think I'll leave that one alone right there. Hopefully that's enough to get you rolling on these 3 problems. Have a great day.